Welcome back, everyone. Today's lecture, we tie everything together. The lecture is called Calorimetry. Definition: it's the process of measuring heat absorbed or released in a chemical reaction or process. When I say heat, you're thinking Q. Okay, quick review. Units of heat are English units, calories, metric units, joules. A calorie is 4.18 joules. A calorie, 1 calorie exactly, infinite number of sig figs. 4.18 joules, 3 sig figs. Goal 1 of the 3 goals today. The first goal, become a master at converting between calories and joules. This by far is the easiest of the 3 goals in today's lecture. So something like question 1, 25.6 calories. I want to go to joules. I'm going to need a conversion factor. 1 calorie, 4.18 joules. I'm going to do the math. I get to 3 sig figs, 107 joules. Okay, I want you to try 2 through 5. Pause the lecture video. When you bring it back up to speed, I'll have my answers on the board. Okay, we're back. Here is my work and the answers. It's the proper number of sig figs. Yeah. And even number 4 is the proper number of sig figs, even though we have 810.5, 4 sig figs there. The 4.18 joules is 3 sig figs, so we're going to express our final answer to 3 sig figs. So I hope that's helpful. Let's move on. Another quick review definition: heat. I say heat, you think Q. Energy that's flowing from hot to cold. We can calculate Q. Q is equal to M times delta T times C, where delta T is T final minus T initial, and M is mass in grams, and C is specific heat, which is different for every substance. So I'm going to have to give you a table of specific heats if I'm going to ask you about substances. The only specific heat that I'm expecting that you know is that liquid water's specific heat is 1 calorie per gram degree C, or 4.18 joules per gram degree C. You're going to use this so often that I think it's just going to seep in your brain whether you try to memorize it or not. Goal number 2, become a Q equals M delta TC expert. And so here's a couple of questions to try that. What is the specific heat of an unknown metal if the temperature of 120 grams of the metal after absorbing 4,675 joules of heat went up by 101.1 degrees Celsius? All right, when I look at that, here's what I see. I see specific heat. That's what I'm after. 120 grams of the metal, that's mass. This heat, that's Q, and went up by 101 degrees C. That's delta T. Okay, and so I'm going to take this Q equals M delta TC equation, and I'm going to solve for C. Rearranging this, C is equal to Q over M times delta T. 4675 joules. If they gave this to me in kilojoules, I would have to change it to joules. Mass, 120.0 grams. Delta T, T final minus T initial. T final is higher, so this is 101.1 degrees Celsius. All right, and when I put that in the calculator, I get 0.385 units, joules per gram degrees Celsius. You will see when you get a table of specific heats. I believe that's the specific heat of copper. I'm not sure. Okay. Number 2, how much heat's required? You try that one, pause the video, show your work, pull up the video again, I'll show you mine. All right, here I've plugged in, looks like I'm after heat, Q. They give me mass, they give me T final, T initial, and they give me specific heat. Plugging those numbers in, I get 2,385 joules is my answer. If you're over 1,000 joules, then in best form, I would want to express that as kilojoules. Let's see, we're down to 3 sig figs, so my final answer is going to be 2.39 kilojoules. All right, let's move on. If I take two different substances, and these substances have very different specific heats, and I add the same amount of heat, the same Q, to the same mass of each of the substances, the substance with the larger specific heat is going to have the smallest temperature change. Okay, that's something that you need to have clear in your head, okay, how this kind of works on an abstract level. So here's some different building materials and their specific heats. Joules per gram degree C and joules per gram degree K are the same thing because the size of a degree C and the size of a degree K are the same. But in this particular example here, this question, I have the same mass for the two materials. I have the same amount of heat for the two materials, and it's asking me which one would have the largest delta T. Okay, and so if I take Q is equal to M delta Tc, first of all, the two substances that I'm kind of going to be focusing on would be, I'm looking at this chart, I'm going to be looking at water as an option with the largest specific heat, and what's the smallest one? Granite with the smallest specific heat. I mean, everything else in between. You know how this game is played. Which one is going to have the biggest? Well, it's going to be either the largest or the smallest specific heats, right? So a couple ways we can do this. One, in a more abstract way, I can say this. If I have the same mass, that variable kind of goes away. And if I have the same amount of heat, that variable goes away. Which one of these substances is going to have the largest delta T? Well, since they're on the same side of the equation, it's going to be the one with the smallest specific heat. So I'm going to go with granite at 0.790 joules per gram degree C as my answer. Now, another way of doing this is you could calculate Q water is equal to mass, technical difficulty there. Mass of water, delta T of the water, specific heat of the water, and then you could calculate Q granite is equal to mass granite delta T, granite specific heat, granite. And you could plug in, 50 grams for the mass, 50 grams for the mass. You could say the same amount of heat, so you could pick some number, 1,000 joules, 1,000 joules. You could put in the specific heats of water and granite and calculate, what gave you the largest delta T. If you wanted to do it just sort of with numbers and less abstract, that would be a good way of doing things. You're going to get the same answer. You're going to get granite with its small specific heat is going to give you the largest change in temperature. I mean, that's what specific heat is. How much energy is needed to raise 1 gram of a substance by 1 degree Celsius. Granite with a relatively low specific heat compared to water it's not going to take as much energy to raise it 1 degree Celsius. So it'll have a larger temperature change. All right, let's move on. There is a device that has a way cooler name, I think, than what it actually does. A bomb calorimeter. Nothing explodes in this, by the way. It's a device used to measure the amount of heat given off when you burn things. And what it is, it's a cup. You can see that cup is called a bomb. And that cup has a sample in it, sitting on that sample cup. Let's say you want to measure how many calories are in a Snicker bar or something like that, right? Then what you could do is you could cut off a small chunk of Snicker bar and actually mass it, and then put that Snicker bar in that sample cup, and then fill that jar, that bomb, shown in figure B, with pure oxygen. And you would have a way of igniting the Snicker bar. You wrap it with ignition wire and you attach it to 2 electrodes, which are attached to a battery. You then submerge that bomb jar that's sealed in a certain volume of water. Okay, you can see that. And that water is evenly mixed, and it has a thermometer in it, so you know the exact temperature of the water. Okay, and what happens then is very precisely, you burn that little chunk of Snicker bar inside that bomb container. All of the heat released when that Snicker bar burns goes through the cup, the bomb cup, into the water, and the water temperature goes up. Okay, you can, in pure oxygen, you can burn things in a fraction of a second. It releases all of its heat as it burns, and all of that heat is transferred to the water around it. In this case, the Snicker bar is the system, and the water around it is the surroundings. Okay, so that's kind of the thinking here. I'm going to do several examples, but we need to define what's happening. What are we observing? What are we paying attention to? Because we're going to calculate delta H for like a Snicker bar burning. And there's a trick involved. I'll show you that the next screen. But it's the same trick we use every single time. And so once you've figured out, you know, what the trick is and why it works, why we're using it, it makes the other problems that we're going to do in your homework and the quiz and the test questions very simple. All right, so that's the idea. Now, why do we have a bomb calorimeter? Well, back to the burning of a Snicker bar. If we want to know Q Snicker bar, that is the heat released when that Snicker bar is burned, that value, by the way, would be negative, right? Negative Q Snicker bar, the negative showing that heat's flowing out of the Snicker bar as it burns. We can't calculate Q Snicker bar directly. We have an equation, Q is equal to m delta Tc, but we would know the mass of the Snicker bar, but when it's on fire, we wouldn't know the change in temperature. And if you just take a thermometer and put it into a flame, you're going to blow that thermometer up. And that won't work. Plus, a Snicker bar is not a pure substance, so it doesn't have a specific heat. It's a mixture of a whole bunch of delicious things, right? So the way that we get Q Snicker bar is we say this. We say negative Q Snicker bar is equal to positive Q water. Let me write that down. Negative Q Snicker bar is equal to positive Q water. Now that's the trick right there. You need to be able to, like in a sentence or two, that would be a really good test question. What does that mean? What that means is negative Q Snicker bar. The heat released when you burn a Snicker bar is completely transferred and absorbed, that's what the plus means, by the water around it. The Snicker bar is the system, the water is the surroundings, and with this highly insulated device called a bomb calorimeter, we don't lose any heat to anywhere else. All of the heat of the Snicker bar, when it's burned, is transferred into the water. Okay, now why is that important? Well, because we can calculate Q water. We can say Q water is mass of the water, delta T of the water, specific heat of the water. Okay, and we're not going to do that on this screen. We'll have several examples coming up, but let's say you have 200 milliliters of water. Well, the density of water is 1 gram per mil, so 200 milliliters of water is 200 grams. Let's say the temperature goes up by 13.0 degrees, from 20 to 33.0 degrees. Delta T is positive 13.0 degrees, and specific heat of liquid water, 4.18 joules per gram degree C. Okay, we could punch those numbers in, and we could get a value for Q water. And then, if we go back up to this top equation, whatever that number is, we can change the sign and call that Q Snicker bar, because the amount of energy released by the Snicker bar is absorbed by the water molecules. Let's look at that in a little more detail in another example. Okay, so that's our third goal. Understand how Q is measured in the lab with a bomb calorimeter, and understand how Q is used to calculate delta H. Remember, delta H is Q per mole, and delta H is always from the system's perspective. So in the previous screen, delta H of a burning Snicker bar would be Q Snicker bar over moles of Snicker bar burned, okay? And that, because Q would be negative, your delta H would be negative, what you'd expect in a combustion, okay? All combustions release heat, and therefore would have a negative delta H. All right, let's do an example that's listed here. We're going to burn a hydrocarbon, a solid decane is what it's called. C10H22 is burned. 4 grams of it is put in that bomb cell, okay, that bomb cup. That cup is sealed and filled with pure oxygen, and then that cup is submerged in a bunch of water. All right, 1.500 liters of water. And when you hit the ignition button, that solid C10H22 ignites, it burns, it releases heat. So the burning C10H22 is my system, and the water is the surroundings. All right, and what we're seeing here is Q. Heat is flowing out of the system into the surroundings. And the reason I know that that's true is the temperature of the water goes up, all right? And so the question A, how much heat was released in this combustion? All right, when I say heat, you're thinking Q. I want to know Q C10H22. I can't get that directly, but I know this. The amount of heat released by the burning of C10H22 is equal to the amount of heat absorbed by the water. And I can calculate Q water, okay? So for my calculations for A, Q water is equal to the mass of the water, delta T of the water, specific heat of the water, okay, which is well, that's 1,500 milliliters, right? And the density of water is 1 gram per milliliter, so that's 1,500 grams of water. Delta T is T final minus T initial, and specific heat of water is 4.18 joules per gram degree C. All right, so when I do that, I get, I'm going to bump the decimal point over 3 places, I get 75.2 kilojoules of heat. is being absorbed by the water, and it also is being released by the burning C10H22. Okay? So if Q water is 75.2 kilojoules, QC10H22 is equal to negative 75.2 kilojoules. It's important that you realize the sign convention here. Positive Q water means the water absorbs that amount of heat. Negative QC10H22 means that that amount of heat is released when that substance is burned. Okay? And then B, what is the heat of combustion in kilojoules per mole? Okay, well that's delta H combustion would be Q C10H22 over moles of C10H22. All right, well, we have the numerator. The numerator is negative 75.2. We just need moles of C10H22, and they don't give us that, but they give us the grams, the mass, and they give us the molar mass, or the formula of the substance. And so we can use molar mass to convert grams to moles. So 12.01 times 10 plus 22 times 1.008. Okay, so to do that, I get 0.028 moles. 0.028 moles. Okay? And when I put that into my calculator, I get 2,674. To 2 sig figs because of the 4.0 grams, I get 2,700 kilojoules per mole, and my answer is negative, which just means every time I burn 1 mole of C10H22, I release 2,700 kilojoules of energy. Okay. Yep. All right, let's move on to another example. This example here is a dissolving equation. Okay, so NaOH is a salt. You know that all salts at room temperature are solids. When you put a salt in water, it dissociates into its ions aqueous with charges. Okay, so just the dissolving process before we even start looks like this. All right, that's how sodium hydroxide dissolves. All right, now I'm looking at the word problem. They give me a mass of sodium hydroxide. They give me a volume of water that it's dissolving in. And they give me a temperature change. It goes up by 1.8 degrees. Calculate delta H for this process, and then write a thermochemical equation. Okay, so the thermochemical equation would be the blue chemical equation that I just have up there with the delta H either off to the side or in the equation. Okay, so the A and B are related to each other. Now remember, for A, delta H is Q per mole. And I'm envisioning this like, okay, we have this cup with water, and we have our NaOH, and it's dissolving, okay? So the NaOH is the system, and the water surrounding it is the surroundings. If the temperature of the water goes up, that means that Q heat is flowing from the NaOH to the water. So NaOH is going to have a negative Q. That just means it's flowing out of the NaOH during the dissolving process. All right, so let's see. QNaOH, this is the trick that we're going to do again. We cannot measure QNaOH directly. We don't have a specific heat for NaOH. We don't have a change in temperature of the NaOH. We have a change in temperature of the surroundings. And so our trick that we're going to use again and again and again is we're going to say this. Positive Q water is equal to negative Q NaOH. Okay? And that is the amount of energy absorbed by the water is going to be equal to the amount of energy released by the NaOH as it dissolves. All right. The reason we're doing that is we can calculate Q water. Q water is mass of water, 250 milliliters, 1 gram per mil density of water. Okay. That's true of anything even made in water. If you see a solution, that solution has a density of 1 gram per mil. Okay, so that's the mass of the water. Delta T is 1.8 degrees Celsius and 4.18 joules per gram degrees Celsius. That's the specific heat of water. Okay. I get, let's see, we're down to 2 sig figs. 1.9 kilojoules for Q water. All right, well that means that QNaOH is negative 1.9 kilojoules, okay, for this reason right here. All right, I'm going to erase that just because I need the space. All right, so we need moles of NaOH, and I can do 15.0 grams NaOH. I can use, let me erase that, that looks horrible. .01 is the molar mass. 0.375 is my moles of NaOH. All right, moles are always positive, okay? All right, when I do the division, negative 1.9 divided by 0.375, my answer is 5.1, negative 5.1 kilojoules per mole. That's my answer for A. My answer for B, the thermochemical equation, would look like this. NaOH, solid, when put in water, is going to give me sodium ions, hydroxide ions, both aqueous, and you'll release 5.1 kilojoules of energy for each mole of NaOH that you dissolve. Now, since there's 1 mole of NaOH in this equation, I'll go with 5.1 kilojoules, okay, because it's kilojoules per 1 mole. All right. I hope you're kind of getting comfortable with this a little bit. Let's try another scenario here. All right, this one here is ice melting. And what I'm envisioning is a cup with water and an ice cube in it, okay? And if you think about what's going to happen to this ice to melt it, heat is going to have to flow into the ice from the water to facilitate the phase change. Okay, so the process of melting, the chemical equation would look like this. H2O solid becomes H2O liquid. Now, if I ask you to fall off the fence and say, what side do you think the heat is on? Do I have to add heat to ice to get it to become liquid, or when ice becomes a liquid, it gives off heat? Which one makes more sense? You would say, I think the first one does. I have to add heat to facilitate the phase change, and you'd be right. Okay, well, that heat right here, that is delta H for this process. Okay, you would expect delta H to be a positive value because you'd expect it to go in on the left. Okay, and the ice is the system and the water is the surroundings. So when I ask you to calculate delta H for this process, I'm saying, can you get delta H of the ice, which is Q ice over moles of ice? Okay. All right. What I want you to do is think about the last two examples, kind of the process, the approach I took to break this down. How are you going to get Q ice? Remember, there's a trick involved there. How are you going to get moles of ice? Find those two values, plug them in, do the division, come up with delta H of ice. Try your work, show your work, and then start the video back up, and I'll show you my results. Okay, so for this example, the ice is the system, the water is the surroundings. The trick that I'm talking about is right here. We can't measure Q ice directly. We can never measure Q system directly. We have to measure Q surroundings, assume that we lose no heat, change the sign, and then call that Q system. So we're going to calculate Q water, and then we're going to change the sign and call that Q ice. Okay, the reason we're doing that, delta H ice is equal to Q ice over moles of ice. That's our answer for calculate delta H for the process. All right, so here I'm calculating Q water. I'm using the mass of the water. Okay, now this is one of the top mistakes on the next test. If you're calculating Q liquid water, you have to use the mass of the liquid water. Now it's a little confusing because the mass of the liquid water is given to you in volume here, in milliliters. You need to recognize that liquid water has a density of 1 gram per milliliter and convert 500 milliliters to 500 grams. It's really easy on a test to be flying through this. I'm looking for a mass, boom, there's a mass, put 10 grams there. That's wrong because you're calculating Q liquid water. You need the mass of the liquid water, not the mass of the ice. Okay. Change in temperature of the water, T final minus T initial. Specific heat of liquid water, the one you know, 4.18. When you do the math and bump it over to 3 decimal places and call it kilojoules, I get a negative 3.34 kilojoules. What does that mean? That negative sign there means that heat is flowing out of the liquid water. That's what we said here with the red arrow. Heat is flowing out of the liquid water into the ice to facilitate this change of state of ice as it melts. All right, so we have Q water. We can change its sign. Q ice would be positive 3.34 kilojoules. We just now need moles of ice. Okay, we can get moles of ice by taking the mass of the ice, molar mass of ice, which is molar mass of water, to get moles. All right, then we do the division, and I get delta H for the melting of ice is positive 6.02 kilojoules per mole. What does that mean? That means to melt 1 mole of ice, I need to add 6.02 kilojoules to it. And that amount of energy is going to come from the water around it, from the surroundings, and you would expect the temperature of the ice to stay the same because it's on that flat part of the heating cooling curve. It's melting, that's a potential energy change. There's no change in temperature in a phase change, and you would expect the temperature of the water to go down because it's losing that amount of heat per mole of ice that it's melting, and you can see the temperature does go down. Okay. The last thing is asked here, then write a thermochemical equation for the process. Okay, well, melting ice is going to be H2O solid going to H2O liquid, and then to make that a thermochemical equation, I'm going to put that delta H ice in, since it's positive, on the left-hand side, and there's my thermochemical equation. Okay? All right, you can see, even though there's a lot of different ways that you can apply this, calculation of delta H, Q system per moles of system, it all kind of works the same way. We're always talking from the system's perspective. We can never measure Q system directly. We have to measure Q surroundings, assume we lose no heat and change the sign, and then divide by moles of the system to get delta H. Let's try another one. You're going to see it works exactly the same way. All right, this is the silver tree lab that you did, lab 2, where we took solid copper wire, put it in silver nitrate solution, and we collected silver and we formed copper 2 nitrate. Okay, this is a chemical equation. I want you to rewrite this equation right here as a thermochemical equation, which means I need to find delta H for this equation. Now, if you're putting copper wire into a aqueous silver nitrate solution, the copper wire is your system, and the aqueous silver nitrate around it is the surroundings. Remember, we always do delta H from the system's perspective, so for this example, I'm asking you to calculate delta H of the copper, which would be Q copper over moles of copper. Okay? All right, so let's just diagram a couple of things here and see how you do. This is mass of copper. This is mass of the water, 200.0 grams. This is delta T of the water. And we know, just from what we've been talking about, our trick that I keep referencing, Q copper and Q AgNO3 solution are it's the same amount of heat. Let's see now, if the temperature of the silver nitrate solution goes up, that means heat is flowing out of the copper into the silver nitrate. So that's the trick right there. Negative Q copper, the amount of heat released by the copper in this single replacement reaction, is equal to positive Q silver nitrate, the amount of heat absorbed by the silver nitrate solution. Now, when you see the word aqueous or the word solution, you know that it's 99.9% or more water. So the specific heat of any aqueous solution would be the same as the specific heat of water. Okay? What I want you to do is try to calculate delta H copper on your own with this information and the knowledge that you've gained from this lecture. So turn off the lecture video, try it, join me again, and I will show you my work and explanation. Okay, in this example here, I'm calculating Q silver nitrate solution. 200 milliliters is 200 grams. Delta T, T final minus T initial, is positive 4.4 degrees Celsius. Specific heat of any solution, silver nitrate, would be silver nitrate dissolved in a lot of water. It's the same as the specific heat of water, 4.18. All right, so Q silver nitrate is 3.7 kilojoules. Moles of copper, I'm taking 5.50 grams of copper times the atomic weight of copper to get the number of moles of copper. All right, when I plug those numbers in, the 0.0866 moles of copper in the denominator, and let's try that again, 0.0866 moles copper, negative 3.7 kilojoules. Okay, if Q silver nitrate is positive 3.7, then Q copper is negative 3.7. That just means heat is released from the copper and is flowing into the silver nitrate. okay? I get an answer of negative 43 kilojoules per mole. That's delta H from the copper perspective. Heat, every time I react 1 mole of copper in this reaction, it releases 43 kilojoules of heat. Okay, calculate the change in enthalpy for this reaction. Okay, we did that. Then write down the reaction as a thermochemical equation. Okay, well, I'm going to use the equation typed on the top. And to make it a thermochemical equation, I'm just going to add my delta H into the equation. The fact that delta H is negative means when I put it in the equation, it is positive on the right-hand side. That's how you do it. All right. Last one. This is a single replacement reaction. Aluminum reacting with hydrochloric acid. I'm going to make H2 gas, and I'm going to form soluble aluminum chloride, AlCl3. All right, so we need a 6 here, a 3 here, a 2 there, and a 2 there. That's the chemical equation. When I read the numbers in the word problem, I can see that this is mass of the aluminum, that this is the mass of the HCl, 400.0 grams, and the temperature of the HCl, it goes up by 12 degrees. Okay, that means that heat is flowing out of the aluminum into the hydrochloric acid to give you a positive QHCl. All right, we're going to use 4.18 for the specific heat of any acid solution because solutions are 99.9% water. And the density of the acid is 1 gram per mil. That's how we got up here. That's how we got 400 grams instead of 400 milliliters for the mass of the acid. All right, so it says calculate delta H and then write the thermochemical equation. Okay, well, here's the chemical equation. I want you to write, I want you to calculate delta H for this. The aluminum's the system, the hydrochloric acid is the surroundings. Give it a try and then unpause the video and take a look at my work. All right, so here's my thinking here. Negative Q aluminum, the amount of heat flowing out of the aluminum, was absorbed by the HCl. That's our trick. We can't measure Q aluminum directly. Q system we can never get directly. We have to measure Q surroundings, or calculate Q surroundings. Assume we lose no heat, change the sign, and that'll give us Q system. So Q surroundings is the mass of the surroundings. 400 milliliters of the acid is 400 grams. Change in temperature of the surroundings from the word problem, 12.0 degrees Celsius. Specific heat of the hydrochloric acid solution, same as water, 4.18. Okay, 3 sig figs, 20.1 kilojoules for QHCl. Moles of aluminum would be the weight of the aluminum that was used in the reaction times the atomic weight of aluminum. That'll give us moles. All right, we can calculate delta H of our system, aluminum, is Q aluminum over moles of aluminum. Q aluminum is negative 20.1 kilojoules because QHCl is positive 20.1. And we assume that we lose no heat. And we're going to divide that by moles of aluminum, 0.0946 moles, and we get 3 sig figs, negative 212. Okay, that's my delta H. You can either write the thermochemical equation with it like this. Delta H is negative 212 kilojoules per mole, and that would be fine. Or you could put the delta H in the word problem. And when I put it in the word problem, because it was negative when it was outside, it goes in on the right-hand side. But notice, this is the amount of heat released when 1 mole of aluminum is reacted. And since we have 2 moles of aluminum here, I'm going to release twice as much heat. So I have to take this number and double it, put it here. Okay? So this, when 2 moles of aluminum reacts, not only will I produce this and this, but I'll also produce 425 kilojoules of heat. All right. Well, that's kind of the ideas that you're going to need for this problem, homework problem set, and that's kind of the scope of what the next quiz is going to be like, the calorimetry quiz. So try the homework, check out the answer keys, hit me up, send me an email if you have questions clarifying how to do this, where did this number come from, that kind of thing. I'd be happy to help you out. Good luck with this, and it's been good giving you this lecture. It's one of my favorites, so I hope you enjoyed it. Have a good day, you guys. Oh, I should say, the end. Have a good day, everyone. Goodbye.